All right, welcome to today's live stream. We have Nik doing some live science with us on the topic of non-locality and quantum mechanics and some hypergraph related stuff. And say it again, PR boxes.
Yeah, PR boxes, non-locality, like all kind of quantum games. Hold on. Let me,
All right.
Yeah.
Oh, whoops.
Okay. Let me
All right, let's go for
share.
it.
Okay.
I think you
There
got
you go.
the chat up on your screen there, Dugan, in the
I
middle of
took
the
it away. Yeah,
Okay, good.
that's my bad.
All right. Okay. So what are the non-local games, right? And why they're non-local? It's like I kind of tend to imagine it usually with two kind of parties. You have Alice and Bob, and in this kind of scenario, I always imagine them like sitting in some kind of separated prison boxes, prison cells, or maybe separated on two opposite sides of galaxies, even not necessarily having like a single wall, but actual distance, very large distance separation between them, and then trying to, in some sort of, establish some sort of communication or play some rule that is managed by some kind of referee in this case, usually called Charlie, because Alice, Bob, and Charlie, right? And so in this kind of AI generated image, you can see that there's like Alice and Bob, they try and throw out some coins, and there's like Charlie monitoring them and trying to judge whether they win or lose at that particular game, right? So the most famous game, well, usually those kind of games, they're kind of have this simple setup, right? You have Alice and Bob, they have some corresponding inputs. In the most simple case, they just have some binary input. It could come from Charlie, or they could have just thrown a coin, but usually just some random input. So we have some Alice can get some coin, so it can show that it's like Alice's coin, it has some head and tail, so white and black faces, right? Bob has corresponding input as a coin, and the point of the gate of the game, or according to some rules, that they should generate some output, right? So, and then the judge in the form of Charlie should, according to some rules, determine whether they win or lose, right? Based on the inputs and the outputs of the Alice and Bob, right? But the whole point is that Alice and Bob can't communicate with each other, but they can share some predetermined resources, right? So that this kind of dashed line represents. They can't send some signals because they separated by a large distance, but they can share some resource, some random resource, maybe some kind of log that they wrote down, predetermined log of random events. For example, they have some strategy that you should output like first iterations of a game. For example, they output this, and Alice should output this, Bob should output that. Next 10 iterations, they output something else, right? So they can just share this kind of random log, or they can share some quantum resources, like an actual quantum entangled particles, and they can perform some quantum measurements and quantum experiments on top of those particles, and that's how they can determine what would be their outcomes in order to establish their situation, whether they win or lose. Okay, right, and like this is an actual circuit, for example, that represents the most famous of this kind of non-local case in the form of the quantum circuit. And the rule of that game is usually like it is formulated with this formula, but in words it's very simple. It essentially means that Alice and Bob should output always the same outcome, no matter what input were, instead of a single case where the input was like all heads, right? For example, when Alice and Bob both get black coins, black faces of the coin, like this A and this B, then they should output different results, right? So this is kind of the rule in this case. They always should output the same one, except that single case when the input are all black, right? So that's like how we can interpret it as a Boolean formula, essentially say if X and Y are the inputs, right? So this is like conjugation means and. So this right-hand side always gonna produce 0 if it's the binary inputs, unless X and Y is 1, right? So just and multiplication. So just multiply X and Y, and it only can result in 1 when X and Y equals 1, right? And A and B are actually like that's the symbol for XOR, or excluded disjunction or essentially like a plus modulo 2. Right, so well, it's pretty hard to follow what it actually means, but in words I already told you what it is. So we can actually just enumerate all of the possible scenarios. In this case, because all the inputs and outputs are all binary, there are in total 16 possible scenarios of that particular games. And you can see that if, for example, each row represents different input for Alice and Bob, and you can see if the coins are not all black, then they win if they output the same result, the same outcome. So it's like, for example, in this case, Alice and Bob win because they output the same result, the same answer, or they have this produce the same outcome, right? So they can either output blue or red, doesn't matter, it just have to be the same. And it's the same for the first 3 rows, but the last row is the opposite. They have to produce different outcomes, so they only win in these 2 scenarios. So this kind of the rule of the game, right? So how do you play this game in order to maximize your chances? Because that's the whole point, right? How is it even possible to win perfectly, or maybe to some degree, if you just if you're one of the players? How do you organize your strategy?
So what does black and white mean here, and what does red and blue mean here?
Well, it means, well, just to distinguish between those 2 different binary outcomes, right? White and black, it's for the inputs, right? It represents the inputs to these boxes that Alice and Bob can share, right? So there are 2 inputs to Alice's machines, and you have the same kind of thing for Bob, and blue and red represent the outcomes, or the answers. So you can think it's like the white and black are the result of the coin toss, because it can be random, right? Maybe we want to determine whether they win or lose for all possible scenarios, so we can generate the inputs randomly, right? So we can imagine them throwing some fair coin, and then they just have to output some answer, say yes or no, or just 1, 0, whatever. There's some binary outcome. So that's what red and blue and red represents. Okay.
Is there any notion that it came in, and it came out with the same value?
Well, it can be the output can be equal to the input. It's not kind of restricted. For example, it's like this scenario. For example, if you make a correspondence between black and blue, white and red. So, for example, you can make this kind of scenario, right? But it's just one outcome, just possible scenario that this game can generate. But there are in total 16 of them, depending what Alice can do and what Bob can do.
Right. So
Depending
I guess
on what
it could be that a white A means like, oh, Alice had an input of false,
0.
and the blue
false
means
0.
an output of false. So it's just distinguishing input from output.
Yeah. Yeah. So blue and red, and this larger circles is just to distinguish outcomes from the outputs from the inputs.
Okay, I got it.
So that's
yeah.
But A and B to distinguish Alice and Bob. So it's just to make things different.
And the outcomes at the bottom, the check and the cross. I mean, that's yes and no. That, I mean, you're applying a test to the configuration of the inputs and outputs for a scenario.
Yeah.
So there's 16 scenarios.
Yeah, 16 scenarios, and there's some function for both from given inputs and outputs, the condition whether they lose them or they win. So it's like a binary functions of 4 variables, 2 inputs and 2 outputs.
Yeah, yeah. And then the binary function that you're implementing here is the scroll up. It's like this. You want the exclusive OR of the inputs equaling, does that equal the AND conjunction of the output variables?
Yes. Yeah.
So that'd be like,
So that's the Boolean function. Which you like, this is, you can think of this table as essentially as a Boolean table for that function, right? I guess we can generate one. Let me try. There's an IC source function that generates Boolean. Or maybe it's called truth table. let's see what it does. Yeah, like this. So essentially
Oh,
just
nice.
partitioned 4x4 Boolean table like this. So
Mhm.
if true corresponds to a win condition, and false corresponds to the lose condition. So this is just more to distinguish
Yeah.
all the pieces from each other. All right, so how do you actually play this game or try to win at this game? So turns out you can construct this hypothetical device that that Alice and Bob can share between each other, and so that they can use this device to win perfectly, right? At this game, it looks like essentially all it does. You have to generate this 2x2 box where each of those sections, right? The rows and columns are the inputs, right? And those 4 compartments correspond to actual results when they should win, right? So it's kind of obvious. You have like when the inputs are not 1 and 1, not black, you have to output the same result. So those compartments, the only thing that is allowed to win are when the Alice and Bob actually have the same outputs, right? So just generate this kind of distribution. It's not really distribution, it's almost like you just encode whatever is allowed by the rules of the game, right? So if this box is constructible, well, it's not just enough to construct it. Obviously, construct this box physically by just putting the corresponding points or colored bolt in those compartments to represent those distribution. But it also matters how this box is being manipulated by Alice and Bob in some local manner without signaling between each other and all that, right? But if the first step is just to, in some sense, to generate this win condition. So this distribution on its own just corresponds to maximal winning probability at this game. So if you actually check this condition that we just described previously and take this distribution, plug it into this condition and compute what is the probability of winning, you get 1, right? So they're gonna, if this is the actual probability distribution that Alice and Bob can have access to, they can win 100% of the time, right? But the question is not whether they have access to it, but how is it actually realized in real world, right? So in a way, you can also look at this distribution like this, right? It's just another way of representing the same all the possible winning conditions. So we have the 16. It's essentially the same truth table, but now we can represent it by probability because maybe you're not gonna win perfectly, right? So maybe it's like some fuzzy probability of winning, so that this histogram probabilities are not perfect like that. But the perfect probability would look like this, because just you only have non-zero probability of scenario happening when Alice and Bob win at the game, right? But when you want to construct this kind of scenario in real life, usually you have to, that's what I try to emphasize when I was talking about Alice and Bob sharing resources, right? You actually don't actually have this predetermined probability distribution. You have to construct it, and the way you have to construct it is in the following sense. The only way you have to construct it, you just Alice and Bob are allowed to share some kind of resource, right? You can diagrammatically represent it by this, and the inputs are something that controls their secret boxes, right? They have some machines available to them that they can be controlled by the inputs so that they can manipulate their shared resources and provide an outcome. So that's kind of the circuit diagram that represents what actually can be constructed. So of course, this is like very abstract boxes. It's not, right? It doesn't guarantee that you can use those boxes to construct this probability distribution. And the fact of the matter that you can't do it like classically, even quantumly, using quantum machines like actual quantum computation and quantum gates, you can construct this perfect distribution. But you can construct like a bit fuzzier version of that, which I'm going to show later. Right? But just now I'm going to also make a comment about what does it mean actually not to be able to signal of Alice and Bob not signaling and sending signals to each other. There's like it's just a at the end of the day, it's just one criteria or one constraint for the distribution, right? If you want to analyze all possible boxes by just how their corresponding distributions look like. The condition for non-signaling is just one possible constraint on that probability distribution. So it's like completely device agnostic, like people like to say. We don't describe how it can be constructed. We just say, okay, if that were the inputs and that were the outputs, right? So we describe the joint distribution, and then we can describe, assign some properties to that distribution. Okay, and non-signaling is just one other property that you can compute given the distribution like that. So essentially just this bar heights of your histogram, right? So you can compute it, but there are much more properties like that you can just describe. Like there's all possible, like in the literature, like this is the one of the very comprehensive one by Michael Ury, which is actually made some nice talk at the Wolfram Tech conference of all the places about this, right? So it's like made by some Wolfram fan, and he very comprehensively studied it and all the properties of these distributions. So you can obviously compute some obvious ones that whether your distribution is non-signaling, whether it's non-contextual, whether you can factorize it, inputs and outputs of Alice and Bob are completely independent of each other. So there's all of this kind of properties, and they have some set inclusion kind of graph you can combine. You know how they fit is inside each other, and you can see that the quantum theory, quantum mechanics, it's kind of odd one out. It's like completely can't be described by all those kind of properties. So if you just give me a distribution, it's like there's no nice property of that distribution that tells me exactly, okay, that's the kind of thing that can be produced by quantum theory. So it's like none of those property can single out the quantum mechanics. So that's kind of the problem that people try to solve.
Can I just ask some questions here? So 6 and 7,
Yeah.
are they linked somehow, and what does the color change represent?
Yeah, so I think like 6 and 7, like red means it's somehow weaker than quantum theory, and green means it's stronger. And so you can see that the green ones contain some kind of fast and light signaling things. That's completely non-physical, right? So as soon as you have a distribution that determines that it looks like Alice and Bob send some signal, and that signal is like essentially can be used to send the information, right? So it's like faster than light. So that's the
would wormhole like spin like holes in space-time, would that fall under fast and light signaling? Like
it's hard to say. It's like the different kind of wormholes. Maybe it's a non-traversable one. It's not quite sure because I'm not an expert. It's like what actual wormholes are allowed to be constructed in general relativity. It's like it seems like there's some of them are non-traversable, some of them traversable. It's unclear whether you can send the actual signal through the wormhole. I don't know, right? But if that hypothesis of whether entanglement is equals ER equals CPR conjecture, so that the entanglement equals to some kind of curvature of spacetime in the form of a wormhole, then maybe that's essentially what's happening. But I don't know, just looking, but we are just dealing with some simple things. We're just trying to determine from the shape of distribution, assigning some properties, whether it's like, can you some property single out the quantum theory? And the point is that it's not. So there's like the most popular one is like defining what does it mean to be contextual and non-contextual, which is essentially whether the outcomes depend on the measurement, choice of measurement, some kind of dependency that you can just formulate in terms of probability, and it's not enough, which means it's like you can come up with some distributions that contextual, right? Which means it's kind of but stronger than quantum mechanics, or non-contextual that are much weaker or something like that. And essentially, like there's some counterexamples to all those different combinations. Right. And in the same paper, you can just actually plot all of those different results, like all of the different properties. And you can see that quantum mechanics has a very weird shape, right? And if you plot all those different other combinations, like if you want to describe what are the shape, this geometry of models that are factorizable, contextual, local, non-local combinations of those, they have no shape as a quantum theory does, right? So but you can see the relationship. It's like, for example, the relationship between non-contextual quantum mechanics. You can see that there's a places when the non-contextual kind of goes outside of the quantum theory, and there are some places when it's the other way around. So it's essentially so that's where the counterexample models live. So counterexample probability distributions. Yeah. Now there's like I've looked recently into some more modern studies and research what people are doing. They're trying to close this gap to actually determine what singles out the quantum theory from all of those probability distributions. They're getting close, but it's still unknown, right? There's like the most nice result, the most interesting result that like people know. The point that we are studying non-signaling boxes, non-signaling models. So in a way, because quantum mechanics is non-signaling, it doesn't mean that stronger models, even though they are non-local, it doesn't mean they can exist. So in a way, the interesting thing that there are non-local, non-signaling boxes that stronger than quantum mechanics. Right? So you kind of so quantum mechanics is not the most powerful device that can be constructed in a way of computing stuff or communicating with each other. So there's some kind of constraint that we don't know about, that quantum mechanics is not allowing us to go beyond it, right? And they, like, for example, there's some boxes, like what this like dark green region corresponds to. It corresponds to some PR boxes, which is like this hypothetical device that we've constructed that has these perfect distributions that allows Alice and Bob to win every time, right? This is like this is the Popescu-Rolik box, which corresponds to this point, a single extreme point that allows you to win at CHSH game with 100% probability. But there are some boxes, also non-signaling boxes, non-local boxes, that this kind of represents some non-reliable PR box, which can only work like at some 91% probability, so it can fail. 99% of the time it can fail, but it can still allow to do something, and it says collapsing. So what it allows you to do, to collapse so-called communication complexity, which is kind of a very cool concept, I believe. It's like, essentially, it means that even though it's non-signaling, it still allows you to send communication in the most efficient way possible. It's like, for example, what it exactly means is like if Alice and Bob tries to compute some Boolean function of their inputs, right? Maybe their inputs have many bits, but they just try to compute Boolean function with a single bit output. In general, in order to compute it, there has to be a communication, right? So depending on how many bits, Bob has to maybe send all of the bits to Alice in order to compute that. But when they have access to these PR boxes, even those faulty ones that can fail 90% of the time, they can still collapse this communication complexity so that it can be done using just sending by a single classical bit, right? So there's some complicated Boolean function that maybe depends on hundreds and millions of input bits that only shared, like stored locally for Alice and Bob. Like, for example, they want to compute some dot product. For example, like Alice has x1, right? Bob has y1. They want to compute this kind of function, right? It can also be formulated mod 2, right? So this is like so. So this kind of function requires to Bob to send all of his bits in order to be computed. But when they share this hypothetical boxes, even faulty ones, Bob is only, or Alice can only send a single bit in order to compute it. So there has this collapse of communication complexity, right? So, but it sits like not. It's kind of, there's still a gap between these boxes and quantum mechanics. So it's still unknown whether they're because quantum mechanics probably doesn't collapse the communication complexity. So you still have to send all the bits from Alice to Bob in order to compute this dot product, right? But it is not. But this here it is collapses. So this gap is still unexplained. But people are trying to like construct all kinds of different boxes, so that you narrow this gap and define some boxes that actually collapsing but have some higher probability of being faulty, right? So you can lose much more often, but you can still collapse the communication, right? So this kind of research is very interesting that is going on.
So can I just ask some questions here? So at the bottom, is that probability of winning? So you've got 0.5 up till, wait, so it's probability of winning, and then there's probability of winning on the y-axis.
There's some weird way they plot these diagrams. We only usually care about this y diagram here, y-axis, winning on this CHSH game, but they also like to plot this areas because it's not interesting to plot it on a single axis. And so they formulate this dual CHSH game, essentially just flip the condition of winning or losing, right? And you can compute the winning probability of that dual game. So that you can, like, given a box like that, right? That with some certain probability of winning a CHSH game in the usual way.
Yeah.
But if you flip those winning and losing conditions, like just flip all these check marks and like stop signs, right? Right. If you flip those, you get a dual CHSH rule, or like that's what. It's just like another rule of the game, right? So essentially, you are plotting those boxes on two axes corresponding to different games, right?
Okay.
This game and dual to it.
Okay. I have
Okay.
another quick question there about these shapes. If you scroll up to the image above this one. So these are 3D spaces. And then what does it mean to be at a different point in these spaces? Is that an outcome? Is that like a probability? What is that? Okay.
Well, I lost my connection for a sec. Can you repeat what was the question?
Oh, yeah. So the question is, these are 3D spaces, and then what does it mean to be a point in the space? Is that your probability of different outcomes? And why does it need to be 3D?
No, this one's actually, as I remember it's 3D spaces, but it actually just slices for the 4D space, right? And the 4D space, four-dimensional space here is just represents 4 different correlations that you can compute. So it's not just computing probability, you can compute essentially 4 different correlations, which like were usually used in Bell inequalities, all this kind of stuff. There are 4 different quantities that can be computed from the probability distribution above. So that means it forms a 4-dimensional space, and then you just plot different slices for it.
Okay, so the different boxes are different slices of that 4D space.
Yeah.
And
so and a point in that space essentially show you what the correlations of that probability distribution. So just 4 different quantities that you can just directly compute given those heights of those charts, bars in the bar chart for the distribution. Yeah. And just to show explicitly what the non-signaling condition means, because it's the interesting ones, I think. It's like, yeah, given that distribution, right, the perfect one can actually construct the categorical distribution. If you marginalize, for example, this case, only show all the variables except Alice in this case, right? Alice's outcome, you marginalize it over. You can see that the distribution now completely uniform. So it's like 1, 8, 1, 8, 1, 8, 1, 8. It essentially means that no matter which input Alice gets, all the Bob outcomes and inputs are completely independent. So it's like that's essentially how you, in probability terms, encode what does it mean to non-signal to each other. It means that no matter what's the input, Bob can't distinguish them, right? So Alice gets heads or tails, 1 or 0. His distributions of both input and output is just the same. It doesn't have to be uniform, but the point is that these first four numbers are the same as these first 4 numbers. So that's like just the condition of the probability distribution. So they're the same. All right. So let's just continue. So when I construct this kind of boxes, this is kind of things I imagine because of the hypothetical boxes, right? And we are trying to think whether it's possible to construct them in real life. So in this particular case, you don't have to actually store probability distribution in each of the compartments like here, right? You can imagine if there is a probability distribution, you can just sample one of the possible outcomes. So they actually make a box with the possible things that Bob and Alice can reach into and grab out of that box, and that's gonna be their answer, right? So that's you can represent. So this kind of the box corresponding to these PR boxes, one of those particular instances, right? You just sample one of those compartments, given those distributions, because it's a perfect box, it's always going to generate a valid solution, valid winning condition. So it means that this box, and this compartment, I guess, are always going to contain the same results, and this the only one that's going to contain the opposite results here, right? So that means no matter which of the compartment Alice and Bob gonna reach into, they always gonna win, right? But how they would decide, like for example, the scenario, how the actual box works, because they actually have to decide in this non-local way of how to actually reach to the same compartment, right? Because that's actually what means, that's what has to happen in order for them to win, right? I imagine that there's like some kind of manipulation that Alice and Bob can apply to this box in order to determine what would be the compartment they reach to. For example, they always imagine that they can always reach and grab the ball, the covered ball, from this top left compartment, right? From this one, where is the red balls for Alice and Bob. But they can manipulate the box in the following manner. For example, if the inputs are black for Alice and Bob, they just swap the corresponding row or the columns of that box. So for example, if Alice gets the black coin, the black input, Alice swaps the rows. So the first row and the second row get swapped if Alice gets the black input, right? And if Bob gets the black input, he swaps the column of that box. So that in this case, the column of this non-swap box gets swapped. And if they both swap, if they both get the black input, they both swap, right? So essentially that would allow them to reach to this box. So they so they kind of know which box to open, which compartment of the box to open. And then when they both get the black input, they always gonna reach into this one, right? Or this one, or this one. But no matter what, they're gonna win. So this kind of hypothetical device would allow them to win. But because it's impossible, it's hard to imagine how to actually construct this kind of box that Alice and Bob can individually swap rows and columns, even though this device is like shared between them while they are separated very far by very large distance. Okay, but yeah, is there any question about this kind of manipulation?
So is the hypothetical scenario here that there's a device that has these box input outputs, and it's like a device that's connected across any amount of distance that, let's just say, has fast inline communication?
Yeah, it's like some kind of device that it's like a black box that appears for Alice and Bob, right? They don't actually see what the insides of the boxes, but they somehow can rotate or flip rows and columns of them, and they only can open the single compartment. So you can imagine this kind of universal gears there that allow them to rotate stuff around, and then just open one of the compartments. So even though Alice manipulating locally their side, like swapping the rows, it still affects the actual box on the Bob side, right? So it's kind of non-local in this sense. So that's why it's non-local, and that's why it's hard to construct and probably impossible. But what
is that a PR box? Is that what a PR box is? With that, or what? That's what it would be.
Yeah, that's like this hypothetical device that sits on the top of this hierarchy that allows you to win 100% of the time, which is just hypothetical box, but it's still non-signaling, right? So because we only study those boxes that don't violate relativity. So,
yeah. Okay.
So it's still powerful box and hypothetical one, but it's no relativity violated. But you can still get close to it, closer than may be expected by using quantum theory and quantum computation, right? And which allows you construct essentially this box, right? So it's not, you can see that it's not quite perfect. It almost looks like that PR box, but it has some fuzziness into it. It's like, oh, there's still some non-zero probability, which is smaller, but non-zero probability actually failing at each of those compartments. But the shape is kind of the same, right? So just the same shape, just with more noise. So that's what actually is allowed to construct using quantum gates and quantum computation. More specifically, you can construct this following circuit and reconstruct it in some lab or whatever that only is allowed to apply some Hadamard gates, depending on your classical inputs. And they share some actual quantum entanglement between them. So the resource is just a single entangled pair of particles, like maybe a pair of electrons or photons that may be not necessarily fully entangled, not necessarily bell pair, but some kind of rotated thing, right? Because where's the circuit? In more detailed circuit, we have like built in here. If you think of this arc, right? This is just a pure entanglement, maximally entangled pair of particles that is usually being produced in all those experiments, but it's like looks a little different because it's locally, there's some rotation on the Bob side, and then they control it differently. But you can kind of just shove it all in this entanglement, right? And just think of the.
Do you want to make it just a little bit bigger?
Oh,
okay, so
this one or this one?
Oh, that's okay.
Okay, that's fine, cars.
Hi guys, good to have been around. Unfortunately, I have to get moving with my meeting schedule. I would have preferred quantum games instead of that, but yeah.
No problem. Thanks, Carlos.
That's a pity because it's like we almost got to the hypergraphs.
Yeah, actually, I mean, I'm gonna wait a little because I still have 5 minutes technically, so I'm gonna hang around for a bit longer.
Yeah, let me speed it up a little bit. Well, let's just jump right there. Right. The point is like, yeah, this is a quantum box. You can do it like this. You can manipulate them. You can compute the probability. It's higher than what you can achieve classically. Whatever, right?
Okay.
But now the point is, what I've tried to do just for fun. It's like we know how these boxes work, right? Imagine that this is the quantum boxes or PR boxes. If I wanted to construct them using rewriting, right, or actually some kind of using space-time atoms in a way, right? Just imagine how that would work, right? So the point is that manipulation that I've described, like Alice and Bob swapping rows and columns, how can you implement it using rewriting rules of the hypergraph? And essentially that's what I came up with. So almost like a straightforward manipulation of the corresponding hypergraph, just instead of that 2x2 box, right? So how this thing works? Okay, it's kind of almost, it's like corresponds to that box, obviously, like almost one-to-one. You just have to read it properly. Like those 4 compartments correspond to these vertices, 1, 2, 3, 4, right? Those appendages to each of those compartments, those are the Alice and Bob particles that they can reach out of each of those individual compartments, and you can distinguish them. The point that you can distinguish them because these hyper edges are slightly different. You can distinguish them by whether this arrow, for example, is greater than this one. So they're both hyper edges with 4 vertices, but they have some different order to those vertices. So that's how you can distinguish those appendages. One belongs to Alice, one belongs to Bob. And you can imagine that these appendages can be written completely independently. Maybe they like also shared as some common interface between them, and they can be by graph rewritings completely separated to different parts of the hypergraph and so on. But so those actual appendages correspond, or rather these vertices correspond to the actual particles, right? And whether it's a red and blue, or it's spin up, spin down, is just represented by this unary edge. If there is an unary edge, for example, it's a spin up or 1. If there's no unary edge, like here, here, or here, that's 0, right? So that's how the colors can be encoded. But now we want to, but what are those loops here? Those loops essentially encode the current active row for Alice, right? So that's what Alice is allowed to manipulate. And those column essentially like encoded differently so that you can differentiate between them, again using unary edges on this square. This is the column that Bob can manipulate. So essentially the rule for Alice to manipulate her side of the box given some input is to swap those loops around, like top it down. It just swaps rows, and Bob just swaps this unary edges left to right, right? So yeah, so that's the box that this hypergraph corresponds to, right? So this is a blue, corresponds to no unary edge here. So it's blue, blue here, blue, red here. So that's the correspondence between this hypergraph and this box. And so now we want to construct the rules that I just described. For the Alice manipulation, just it can look like this. It can operate relative to a single appendage. So it doesn't have to observe all of the compartments. It's kind of the rule operates on its own on a single appendage like that. And it only looks at those loops over there, right? And what it does, it just swaps the loop, right? It goes from top to bottom or bottom to top. And Bob rule is doing the same similar manipulation, but it's doing to this unary edge, right? It swaps it left, right, left, right. And how these rules are constructed, they actually can apply them, you can compose them together. Let me try actually evaluate this. So given those two rules, for example, if you apply Alice's rule to our initial box, those loops go down, okay, right? This is like just a convenience function to apply the rule without all this rewriting information, right? You can apply Bob rule and Alice rule to the box. Now all the both rows and columns are swapped together, but you can apply them at any place. Like, for example, if I apply Bob rule again, that column should go back to the left, right? So it appears here.
Yeah.
So even though our rules are kind of look like that they only swap left to right, what actually happens when it goes back, this rule acts on a different appendage. So it's in a way we're now rewriting not this appendage, but maybe this one. So everything is symmetric. So you actually need to rotate it if you want to see what the actual matching of that left-hand side is. So we have these rules, but the most interesting rules are what happens during measurement, right? So some naive thing is to do is like, okay, what happens when Alice measures her side of her compartment, right? So again, she tries to match her corresponding appendage, and rewrite it to something like distinguishable, to this free-leaf clover thing, right? So it just detaches her particular particle from this interface that they share, right? And also destroys half of the box. It's just a just fun thing. It doesn't have to happen, but this is just one attempt. And Bob measure is also doing something similar, but it like in order to distinguish them, for example, it detaches it as this 4-leaf clover thing, right? So what happens if we apply those? Here, well, this is just showing the manipulation of rows and columns again, but if we apply just Alice measurement without any swapping of the columns, like this particular appendage getting detached, right? So now we can see that Alice measured 1. So it has this 3-leaf clover with the unary edge. If we then apply, if we apply after that, we apply Bob measure. You see, this is only a single place. Yeah, this is like very tricky. What actually happens, because Alice only sees one of the rows, right? It actually detaches both of those. So now it's actually a branching rule. So measurement is branching, so it produces 2 possible outcomes for Alice. So you have a 3-leaf clover either on the left or on the right. Right, and it also destroyed half of the interface, so that it can't measure twice or something like that. This is just one particular implementation, right? But what happens if we after that apply the Bob measurement, right? And it's actually not perfect. There's some problem with that, which kind of later we can try to mitigate. But if we apply Bob measurement, because it only applies to one of the hypergraphs, for example, because we destroyed half of this interface, it only applies here, but it does not apply in here. In a way, so it's kind of self-corrected itself so that it made consistent, because we want to measure the box. We only allowed to take the compartment, the same, to choose the same compartment as Alice did, right? So in a way, the way, because that destruction of the half of the interface is allowed us to do it in a way. But of course, it's like, it's problematic in a sense that if you imagine what actually happened to this branch, right? Because if Alice measured the left appendage in one branch and the right appendage on the second branch, and then Bob tried to measure, of course, in this branch it worked and actually measured this particle, and they successfully achieved the extraction and the measurement so that they can reproduce the correlation that is produced by this particle box. Right? But what happened to here?
So yeah, sorry, Nick, I just have to go now, but that's a very cool application of hypergraph writing. Looking forward to seeing more.
Yeah, awesome. No problem. See you.
See you.
Bye.
All right. So where were we? Yeah. So it's kind of problematic here because what happens to this right branch, the one that, because the way the rule is written is not applied here. The left hand side of that rule of Bob measuring, because of this interface being destroyed, it can't really recover the particle neither from here, neither from here. So it's in a way, in that particular branch, it seems like with this rule implementation, Bob didn't measure anything at all. So it kind of failed. Okay, it's like, but we don't observe it in real life, like, right? If everything is set up perfectly, if they have a nice equipment so that we can, but certainly say that if Alice found the particle, Bob will find the particle, right? So we have to explain the situation.
What if they measured simultaneously? Like, what if the rules were applied simultaneously? Then you'd have like a multi-way of like who measured first, basically.
Well, yeah, that's not appropriate. Like you also allowed to change your frames of reference, right? So in a way, it still works if Bob measures first, right? In the way, this particular example, if we just swap the order of who's measured first, they're still gonna produce the same outcome, right? But now you just from the other perspective, there's still a problem, but from the different perspective. Now, Bob measuring first, like extracting his 4-leaf clover from this top left compartment, right? And from the bottom left. Now, if now Alice's measurement only applies in this scenario, right? So, but that's our implementation, right? So it's still the same kind of problem that what happens to this branch.
Well, isn't that because this is basically representing what happens in like classical reality? Like if one person has measured something, then classically there's no way for the other person to be able to get the information of what the second person measured. So it's kind of like
we're not getting, we're not representing some information transfer here, right? Those are kind of those appendages, like if you actually in the Wolfram physics project context, you imagine that those parts of the hypergraph, like this vertex number 5 and vertex number 6, they can be using rewriting sent to completely different sides of the hypergraph, right? But the point is that this interface is still there, so it's kind of has this curvature embedded into the hypergraph, so it's like a wormhole, somewhat, right? So this is like they already share this interface, even though they are particles quite separated from each other, so that they can show in like there are some many events being applied with those particles interacting with its space, corresponding space, and with this particle interacting with its corresponding space, and that can be separated farther away. And when it's like there's no interaction happening, no noise being applied, this interface is intact.
So maybe I don't understand what you're saying is the problem, but I thought what you're saying is once Alice, for example, makes a measurement, it destroys the ability for like it destroys that that structure, so that whatever measurement Bob makes is not connected. It won't be able to be influenced by the measurement that Alice made, or they won't be able to end up in the same 4-leaf clover.
But yeah, the problem is that there are two branches, right? If you kind of trying to explain it in the usual many word kind of situation explanation, that Alice performed the measurement and both situation happened, right? The only consistent way for Bob, especially when the actual swapping of his corresponding column happens after that, right? You know, it has to be consistent, but how those branches are interacting with each other is not explained. It's like, and as far as as far as I'm aware, many worlds doesn't usually consider those kind of two-party interactions at all. They just explain that what happens during the single measurement, and just okay, they're just trying to explain most of the time, it's just superposition and how probabilities work. But how those kind of entangled scenarios happen in many worlds, it's usually it's not explained very often or very well. I don't know how.
Yeah.
So it's like if you explain, if there are two branches, but what happens in the branch that is inconsistent with the actual measurement, or the one that actually has to happen in order to reproduce all the correlations, it's not clear at all, right? So, and that's why this kind of measurement rule construction fails. So it has this problem, right? But I've tried to fix it. I've just played around, and it's like my second attempt at what's happening. Now it's essentially the same thing, but now we don't destroy the interface. Essentially the same thing, but we keep this wormhole intact, right? So, but there's something interesting happens now. As when you implement this rule instead of the above, when you measure, for example, if you apply, I just use this one. When you apply measurement to the box, you again get the two branches, right? But now because the interface haven't went well, right? If you apply the Bob rule or Bob measurement, now it's like you apply the swap to each of those branches and then measure, it will result in 4 different potential scenarios, right? So, with only one of them being consistent is this one, right? So, in order to reproduce all the correlations that we actually observe in our experiments, they have to be consistent, and those colored balls has to be extracted from the same compartment, right? So that's the only thing that has to happen.
Okay.
So, but so the question now, if measurement works like this, what happens to these 3 branches when the measurement performed by Alice and Bob are not compatible with each other, right? So that's like and the resolution. It's like a fun resolution that you can think of. That there is another rule. It's not implemented, right? But you can imagine that there is another rule acting in this universe. This our tiny universe that we implemented, that acts as a sort of garbage collector, right? For example, what's common between those 3 incompatible branches? This wormhole contains an even number of this like standalone appendages, if you wish, right? Like this one and this one, right? And this one and this one, and this one and this one. But in this universe that is compatible, there is no standalone appendages. So if you imagine a rule that doesn't like the wormholes with this independent appendages attached to different compartments or different frame of references, right? It tries to destroy it and everything in the universe, right? So it's you can apply sort of your anthropic principle in these branches. So what happens when Bob? So yeah, there's 4 branches like happened when Bob and Alice performed their measurement. But why we don't observe this scenario and this scenario? Because we got annihilated in those branches. There's always one branch that survives, so we kind of can apply our survivorship by bias to the problem. But in all the branches that are not incompatible got destroyed. So it's got garbage collected because there's some rule that didn't like the wormhole with those independent appendages and it's kind of just swallowed all the universe around it with the speed of light, so we don't observe it, right?
Wait,
So that's kind of fun scenario, you can imagine.
I like the narrative there. Can you just say it again, maybe like in a summarized way, how that hypothetical garbage collector would work? Are you saying that the single appendage would cause some kind of black hole horizon or something like that?
Something like that. It's like usually there's some sci-fi scenario, or it's right. Maybe you heard about like some bubbles exploding in the universe that can, right? I certainly heard some explanations like that. There's a possible, I know some kind of instability can be created in the universe that just expands with the speed of light and destroys everything around it. So it's impossible to observe because it just hits you with the speed of light, right? And so it's like, and this is that's kind of the same thing, right? Like if there's an entanglement, and the point is that it happens every time measurement happens. So we get killed every instant when every kind of measurement happens in the micro universe. In this, right?
So what causes that? What is the inconsistency here from having a single appendage that causes that self-combustion?
Well, just I'm just imagining there's a rule that just tries to rewrite it, and maybe it creates some kind of special thing that, and there's another rule that tries to propagate it and swallow
That's an
everything.
arbitrary rule. It's not something that's it's not an intuition from this exact diagram here.
Well, it's possible to construct it.
Yeah.
Let me maybe I can even try to construct it now. It's just
it's a hypothetical annihilating rule that exists. It's not one that has to exist based on what you've created here.
Yeah, well, for the actual universe, it's hypothetical, but for this example that you constructed, you can actually make this rule.
It's possible to be made, is what you're saying. It is possible.
Yeah, it's possible. I can draw it right now, maybe. Like I can.
I like this theory. I think I feel like a new quantum theory brewing here. Universal garbage collecting self-annihilation worm black hole worm.
How do you make it? Need to make it ordered. Nah, no. Let me start again. So ordered pages. Right. This is our interface. Right.
Mm-hmm.
Okay. So the only thing that distinguishes those incompatible universes from this one is just this single appendages, right? So they're not always opposite of each other, but it can be just acted on a single one. The point is that in this one there is no single one, but it can be a single one. When the problem is that there's some intermediate reference frame when before bulk measure there is a single appendage, right? So we can't really have a rule that destroys universes when there is a black hole with a single one. There has to be two attached to it. So in a way it's very hard to. Maybe there's no way to make it in a single one. How do you do it like this? Yeah. Okay. It's just a sketch, right? So imagine that it's like this one, the one rule that it has to ignore the appendages, that there are two of them. Maybe there's like you can just enumerate all possible garbage collection rules. I don't think that's why I haven't implemented it, because I haven't come up with a way to make a single rule for this example. So that's why it's tricky. But the point is that you have to make one that only applies in these cases and doesn't apply in this, or in this intermediate case. Well, actually, maybe you can speculate that maybe you can start destroying these universes but because it's not really being destroyed, because maybe there's some recovery is happening. No, it's it's weird. Yeah, it's easier to just destroy everything.
Did you by
without
did you by any chance watch the Loki series where they have this like
Yeah, I did.
what's that thing called? That thing that like spins the many
It was,
worlds with a single thread.
what was it called? I don't know. I don't remember how it's spindle. I don't know how it's
It's like a weave or something like that.
weave. Yeah,
Mm.
right.
No, that's what reminds me of. I'm trying to figure out like what the name of, if there's any existing theories for this, and so some of them is like world pruning in the many worlds interpretation, or like quantum suicide is the, is the definition. Well, there's like quantum garbage collection, maybe. Could be the quantum garbage collector, many worlds garbage collector, garbage collecting world. Makes sense.
No. Broken. Wait. Yeah. So you can imagine something like stupid like that. If it's not complete one, you can imagine that it produces some weird, well, just high order edges are broken. Oh, there's some stupid prototype thing. Sure. Graphics keep changing. Now, how do? Okay, let's make some triangle. And imagine that this is like garbage collecting triangle.
Mhm.
Right? It's like as soon as this happens, right? As soon as it finds a single appendage, like scenario like this, when there's a wormhole with this couple appendages, whatever, it turns it into some kind of triangle. And then there's another rule that whenever there's a triangle, it just swallows everything around it. Right? Maybe it produces more and more triangles like that. But
Yeah,
you can let your imagination go wild here. What happens? Right.
okay.
So well, yeah, that's just a fun thing I've tried.
Very cool. Are you gonna do a community post on this one?
Maybe, yeah.
Okay.
I'll try. I have like 2 ideas brewing right now about the 2 community posts that can be potentially be written. This is one, another one is again about geometry of qubits. So let's see. We'll see.
Awesome. It would also be pretty cool if there was a way to play with those shapes up at the top, where you could like have a slider that takes you through the different slices of that 4-dimensional hypercube in 3D, because then you can actually see how those shapes like morph as you move through the probability space.
Yeah, that's well, I'm pretty sure Michael has some Mathematica code
Mhm.
in his paper.
Yeah, it looks like Mathematica, right?
It is, I'm pretty sure, because where I learned about this work was the Wolfram Tech Conference.
Mm.
It's mostly because Michael is not even like an actual theoretical physicist. He's like some retired engineer from Boeing, something like that, decided to crack the non-contextuality of quantum theory. And it's like for some reason, it's like the most comprehensive study of all these probability properties that I found. They're actually like producing this kind of graph how those related to each other.
Yeah, it's pretty cool to have it laid out like this, where you can actually see what the different approaches are and how they connect to each other.
Yeah.
I don't understand why, like, for example, number 4 and number 7 here, or number 4 more specifically, how does it just appear out of nowhere?
Well, it's not appearing out of nowhere. It's just again, it's just one property that you can compute. For example, like this FCI. I think non-signaling, whatever I call non-signaling, is this RCI. It's just called differently in that paper. Remote context independence. That's what I've tried to explain with these probabilities, that they're independent of each other no matter which the input to the other party is, right? So it's essentially equivalent to non-signaling. It's just maybe this is more specific
it-
name for it.
It links to number 13 there. So 12 and 13 have similar names. They're just swapping outcome and context.
Yes, yeah. Context is like input and outcome is like this output from the box.
So why would quantum mechanics not lead to outcome independence?
Well, it doesn't say doesn't mean it doesn't lead to.
Like in other words, the fact that quantum mechanics is only linked to remote context independence.
Well, it's not showing the links, but it's showing the set inclusion. So it means that if there's an arrow, it means all the models, quantum theory, are included in all these models. So you can say that all the quantum mechanical models are context independent, but not all of them not all context independent models are quantum mechanical.
Okay, sure. So then my question is, are there no outcome independent models that are quantum mechanics that use quantum mechanics?
Well, from this graph, I think it's a known. It doesn't mean that. It may be it just only means that it's not strictly included in each other. There's some, I think, let me try to find the paper. Yeah, the paper has a bunch of Venn diagrams like that. Essentially means
Like
when you have an arrow, then you have this inclusion of one thing in another, but they can also be intersecting.
Can you zoom in a bit there? It's like very small. There we go. Okay.
Yeah. Well, maybe there's some other Venn diagrams better than that. Hold on, let me find.
Wow.
Okay. I can remember some better Venn diagrams. Not this one. No, maybe this. You see, like this QM and non-contextual thing. You see, they kind of both included in these types of models, but they intersect each other. So there are models that are both non-contextual and quantum mechanical, but they're not strictly included in one into another. That's why there's no arrow between them.
Yeah, so that was just my question, is that there are no quantum mechanics models that are outcome independent, remote outcome independent. In other words, that number 13 box there.
Yeah. No, it doesn't mean that.
Right.
Yeah, like outcome independence. Yeah, I don't have a good answer for it. There's a lot of properties, and I don't quite remember. Have to actually think about what does it mean in terms of probability. It's not even clear. Well, it's kind of the same way. I think it's the outcome and context independence. I think it's whatever I've showed here using this, essentially because there's no free here. I marginalized Alice outcome. So the fact that this is all the distributions are independent of the out as input, that shows context independent, right? But if I were, instead of free, I marginalized the input instead. Hold on. How do I do this? Alice and Bob. Oh yeah. Maybe I should put it here. Or rather. Well, how do you show it? Oh yeah. 3, 2, 4. And so we're again looking at both probability distributions and Alice outcomes. And those probability distributions are different. If they were the same, like these 4 numbers were the same as these 4 numbers in the same order, that would mean those distribution does not depend on the Alice outcome. So that would mean outcome independence. Right. So this particular model is not outcome independent. So it's stronger. this kind of scenarios. Yeah, whatever. it's those are very complicated concepts.
It's interesting.
Yeah.
So are we saying that there's no quantum model that can account for this type of distribution?
Perhaps.
Maybe that's not the right framing, but yeah, it's just interesting to compare these different things because yeah, there's ways you can structure this that are not necessarily quantum mechanical, which is kind of interesting.
Yeah, it's like only also phrased a little bit weirdly, I believe. It's like, for example, if I clearly remember that this is non-signaling, but the wording of it means that it's the way that it's framed, it's like it's stronger than quantum mechanics has to be, right? So it's in a way you have to signal. So it's like this box should be dependence called some other way around. So that's why it's maybe confusing. So it's a bit confusing. I don't remember how to fix it.
There was an interesting term that I wanted to expand. I don't know if you mentioned it already, but there's this thing called a Fock space. What is the Fock space?
Well, I don't know why you ask it right now. It's just it's completely different thing.
All right. Okay.
It's like, but I can like within the quantum
it's space to do with a separate live stream. Is that something that Garage is presenting tomorrow on Fox Space?
Yeah.
Okay. There we go. Also in the quantum realm, but yeah, that if you guys want to learn about some interesting new terms that I haven't seen before, yeah, tune in for tomorrow's live stream.
Definitely.
Very cool. Okay, thanks for that. Yeah, so as we mentioned, tomorrow's a live stream. We have a project presentation from another summer school alumni. And then we also have an interesting guest presentation on Wednesday, a slightly later time slot than the current one. So definitely tune in for that. That's going to be on neural network potentials and quantum chemistry, I think, or computational chemistry rather. I think that's probably a better way to describe it. So definitely tune in for that one as well. Also, we have a cool book club that's just started. So it's on NKS, which is the current book. So join our Discord, and we're meeting on Sundays to go over NKS. I think we did chapter 4 this last Sunday. Yeah. So chapter 5 will be the next one. So for those who want to catch up and join in with that, yeah, please join us for that. Otherwise, yeah, thanks everyone for attending, and yeah, thanks for the presentation, Nick.
Thank you, Nick.